Hello everyone, welcome to today's webinar which is about Petroleum Engineering Lab Experiment from PioPetro Summer Internship Program. My name is Amina Boudouaya. I'm field operator at Sonatrach Company, Algeria, and I will be your moderator for today's session. Before we start, there is some points need to be highlighted for better enrollment and benefits. First of all your questions should be in Q&A section. The instructor will try to answer them all at the end of the session. Number two, class Zoom capacity is only for 500 participants. If you can't access or miss it, please don't worry, okay? All webinars will be recorded and uploaded on PioPetro YouTube channel. Number three, please don't forget to answer your quiz. You only have 1 week from the deadline. And for any more clarification you need, don't hesitate to reach me through LinkedIn or reach Dr. Ahmed Al. Despite his full schedule, he will do his best to answer. Okay, let me now start to introduce our speaker, Dr. Rehab Elmaghraby, briefly. Dr. Rehab is an associate professor at Faculty of Petroleum and Mining Engineering, Suez University, and she is also an adjunct associate professor at American University in Cairo. She earned her PhD in petroleum engineering from Imperial College London in 2013. Actually, her thesis was about carbon dioxide storage in underground rocks. Dr. Rehab has published over 25 papers, supervises numerous research projects, and has received a Professional Achievement Award from the British Embassy in 2018. Dr. Rehab also serves as a vice chair of the Mining, Petroleum, and Metallurgy section in the General Egyptian Engineering Syndicate, and also she is actively involved in international research and evaluation projects. Guys, believe me, it's not easy at all to summarize her rich career in few lines. So I'm inviting you all to check her profile LinkedIn by yourself. Dr. Rehab, thanks for your coming today. It's a great pleasure to be among us again. Please, you can start now. The mic is yours.
Thanks so much for this introduction. I'm really happy to join you today to talk for 1 hour about the petrochemical engineering laboratory experiments. Hope that you will enjoy and understand the topic. Uh, so let's go together on this short journey. Uh, okay. So when we talk about lab experiment, we have two topics actually to talk about. The first one is to do the laboratory experiment for fluid. So in the reservoir, in normal reservoir, you have oil, you can have gas, and you have water. And you want to know the property of this fluid. This will assess the amount of oil that you have, the quality of oil that you have, or the gas that you have, the water content, the salinity of the water. So there is different, um, uh, important uh, values for knowing this fluid property. Some of these fluid properties, we will talk briefly about the fluid properties. The density, to know more about the density, about the viscosity of this oil, the bubble point pressure that you have is very important in calculation, even um, for calculations, not just measuring experiments. You can also predict it using calculations for the bubble point pressure, oil formation volume factor. You can calculate it using experimental work, or you can use correlation, gas solubility, gas composition, and surface tension. So the simple thing that you know is the density, and actually the value of the crude oil is assessed according to the API of this crude oil. So the first thing that we have, let's talk about crude oil. So you know that the crude oil is a viscous black material or hydrocarbon because it contains hydrogen and carbon, so it is called hydrocarbon. It contains some impurities such as sulfur, nitrogen, and oxygen, and may contain mercury, may contain some heavy metals, but just in the highest amount of highest percent is the hydrocarbon. And the crude oil actually, as you find it in the reservoir, once you produce it, you have to fraction it to different fraction according to the boiling point in the refinery, and this should cover. We will talk briefly about in the next week. Okay, so how can I convert this crude oil to valuable material? And again, I can measure the properties of this material, the line density, the flash point, and so on. But I'm not going to talk about the experiment that we are going to do on the crude oil. I'm sorry, for the petroleum product properties. I'm going to talk about the process, but this is next week. So, so the crude oil, as I told or as I discussed, is very important to know the properties of this crude oil. You can do this using a lab experiment, and this is the favorite one, or you can do using correlation. But actually, you have to have some data available for you in order to do the or to use the correlations. So the dynasty is the easiest one that you can do. You can use one of the apparatus that you are seeing here. This is called the oscillating tube. So you can inject. Let's do one, two. So you can inject here. So this is the port here, and the oscillating tube. You can see the oscillating tube from this window. So you can inject the crude oil, you can inject water, whatever fluid that you have, but not gas. This is not customized for gas. So you have you inject it, and you make sure that there is no bubble, and it is like vibrating and according to oscillating, and according to the oscillation, it's you get a display of the density, and this is very accurate device that you can use and very expensive. But actually, if you can use a hydrometer, and the hydrometer also is customized to measure the density of fluids, just like crude oil and the petroleum products, like kerosene, gasoline, and whatever. So any liquid. So the hydrometer can measure the density and the specific gravity of any liquid. So once we measure the density, we are converting this density to specific gravity, and then we can use convert it to APR. And this is actually the APR, how we evaluate the crude oil. Is it light crude oil, heavy crude oil, and how the worth of this crude oil, is it expensive? Is it no? It will be cheaper. So the grade of this crude oil in the market is one of the important properties to assess this crude oil is the APR. Then the next thing that we can do is the gas solubility. We want to know the amount of gas that we have in this crude oil, and the gas solubility actually is defined as the number of standard cubic feet. So the amount of gas that you have, or the volume of gas that you have at standard cubic feet, that will dissolve in one stock tank barrel of crude oil. I'm assuming that you know these definitions, so I'm not going to go on more detail on these definitions of how it is and the meaning of each one. But in general, we have as the crude oil is produced from the top, we are assuming it's called stock tank barrel of crude oil, and then this is the amount of gas that is dissolved in. So this is one. This is the gas solubility, and then the bubble point pressure, which is actually the highest pressure at which the first bubble of gas appear. And the third one is the oil formation volume factor, and actually it's defined as the volume of oil at reservoir condition divided by volume of oil at standard condition. So why I'm talking about all these three together? Because actually we can use the constant composition expansion test to know them or to experimentally measure them. The bubble point, but also slam tube can be used for bubble point pressure calculation. But anyway, so the bubble point pressure, oil formation volume factors, the gas solubility can all be used using this measured using this experiment. So actually this experiment is based on that you have a constant volume tank with a constant volume, and you have here this is a piston. So this is a piston, and then this is a volume available for the oil with gas dissolved in. So this volume V1 that you have here, so imagine this is a circular accumulator or a circular tank with this volume available for the oil, or you stored a oil with gas dissolved in this oil as volume 1. So this is will be higher than the bubble point pressure because you have gas in. So this is higher than the bubble point pressure. And then you will like retract this accumulator or expand or allow this oil with the gas dissolved in to expand. So now V2 is higher in volume than V1. Again, you will allow it to expand. You will see here there is no gas and oil separation. So until now, this is at lower than the bubble point. I'm sorry, pressure is higher than the bubble point pressure. So the gas will not separate. Again, we will expand it at the pressure. Now we are going to reach the bubble point pressure. And the first bubble, if you have the slant tube, and if you have the container have a transparent window or high pressure window. Okay, you can see the bubble of gas coming out of the oil. So at this point, this is the bubble point pressure. As you decrease the pressure, now you have oil with gas coming out of the oil. And again, you are going to retract it, expand the oil with gas coming out of the oil until you reach the standard condition or the stock tank condition. Okay, right. So what we have now, so we can now, because we can see the bubble forming, we can know that now it is the bubble point. So we can know what is the exact pressure the bubble point formed, or what is separated, the first gas bubble separated from this oil. Oil formation volume factor, because you know the volume of the oil at high pressure, and you know the volume of the oil at, let's revise a bit, the volume of the oil at high pressure and high temperature, the conditions that you have, and know the volume of the oil at standard conditions, so you can calculate the oil formation volume factor. And again, the gas solubility, it is the cubic feet of gas that will dissolve in one stock tank barrel. So if we see that is this will be one stock tank barrel, this will be the amount of gas that is dissolved in. Because we started with no gas and we ended up, so we can know the amount of the gas solubility or the amount of gas that is dissolved in this paper. So just by one test, we can, according to the available, if there is a transparent screen available to see the bubble and so on. So you can do 3 experimental uh, measurement using this test. In normal, if the experiment is not available, you do correlations, and you there is a correlation according if you have the density, if you have the solubility, and so on. You can do some correlation and calculate the oil formation volume factor and so on. The other experiment that we can do, remember, we are talking about fluid properties. So the crude oil viscosity, we can measure the crude oil viscosity using two laboratory experiments, the rolling ball viscometer. So you have, this is actually, it's not a high pressure one. There is a version of it of high pressure, because the favorite things to do is to do this experiment at high pressure, because normally the oil and gas and water is available in the reservoir at high pressure and high temperature, which is a reservoir condition. So it's a Some properties is changing according to the change in pressure. The change in temperature actually will affect this property. Like the viscosity will it change with the change in temperature? Maybe some change, some variation with the pressure, but actually the temperature has a great impact on the viscosity of the crude oil. So it is better to do this experiment at the reservoir condition. But this, if you are doing the experiment at high pressure, it will be more expensive, and the apparatus will be will need pump with high pressure and very very high complications. So you can measure at low pressure and low temperature and still do some correlations and yeah, so you have an indication of what is going. So the rolling ball viscometer, so you have a ball that is rolling. So this, you have this tube filled with crude oil or whatever. It should be transparent, yeah. It's not a, shouldn't be an opaque one to see the ball. But some operators have available facilities to do this for opaque substance like the crude oil. So you have a ball, so you allow this ball to forward, and then you measure the velocity of this ball, you know the diameter of this tube, you know the gravity, you know the density of the ball and the density of the fluid that you have, so you can calculate the viscosity. Okay, so using this equation. So this is called rolling ball discounted. Yeah, here for the surrounding, you can adjust the temperature like a water bath. You can do water in, so you will adjust the temperature, water in and water out. You will adjust the temperature of the surrounding, but still you don't have a high pressure one. So this is because this is the glass one, so it is not customized for high pressure. The other one to do viscosity with a capillary viscometer is a kinematic viscosity. So you have here a viscometer, the glass viscometer, and actually every one is calibrated. And you have you have the you inject the oil. It is placed here in a water bath according to adjust the temperature. Because if you remember, I told you that the main factor affecting the viscosity is the temperature. Okay, so the pressure has a slight impact on the viscosity, but the main factor affecting the temperature, the viscosity is the temperature. This one is for ambient condition, like low pressure, atmospheric pressure. This one is customized for high pressure. Okay, so the higher the pressure, the higher the temperature, the more complicated the device will be. So we have you inject here. You have if you see here, there is two levels. So you increase the crude oil or whatever petroleum product that you have to this level, and you allow to fall here with the change in, and you calculate the time taking, and using equation you can easily calculate this viscosity. Okay, so this is not all the experiment that we can do on the oil and the gas. We can calculate the composition of gas using gas chromatograph. You can do this for high pressure also gas. You can also know the composition of oil using certain type of gas chromatographs. So there is other experiments, many experiments actually you can do for oil and gas, like the flash point. But some of them is very important for the calculations and for the software of the petroleum engineers and for the correlation of the petroleum engineers that they will need, because the more experimental data that you have, even if you are missing one of the data, you can still have accurate results with the correlation. Okay. So the other part that we have here is doing practical lab experiment using rock or rock properties. So the rock that you have, you want to assess the reservoir that you have. Is it what is the amount of oil that you have? What is the porosity of this reservoir? What is the amount of water, the amount of oil, the amount of gas that you have? What is the permeability? Because actually it's going to affect the flow of oil in your reservoir, what is the gas permeability, what is the interfacial tension, the potability, the capillary pressure, the size of the pores inside. Okay, relative permeability. So there is many rock properties. We are not going to cover all of them today, but we are going to talk about porosity, water and oil saturation, liquid permeability, gas permeability, and contact angle. When I say we have to do rock testing, okay, we want to measure the properties of rock. So how I'm going to do so? So I have to get a core. So it is a sample, cylindrical one with a regular shape. You have here like it's like a cylindrical type. So you can know the volume of this sample to test if I want to know the porosity of a rock. So you have to give me a sample. We hold this sample whole block, whole block. Okay, it can be whatever type of cores that you have, sandstone, carbonates, whatever type. But anyway, to do the porosity or to do the test, you have to get a regular shape core block. You can still measure the porosity for irregular shapes, but there is some tests that you cannot do without a regular shape core block. So here, this is the standard 1.5. So the standard for the test that I'm going to talk about is a standard shape core block, which means that it is 1.5 diameter and the length is 3 inch. Okay, so this is the standard core block. You will find if you read about research and you see the tests that they do, you will find that they are doing a standard core plug. So the standard core plug is actually the size, the radius of it with 1.5 inch and the length is 3 inch. Okay. Still, the longer the core plugs that you are doing the test with, the more accurate the result, because there is other factor that will be considered like segregation and so on. But actually, it is the more expensive the core holder will be. It's a harder to get this core plug. So for many usual lab experiment, we are doing this regular core plug. We measure that using a vernier caliper, so it should be. We can calculate the bulk volume that you that for this core plug if it is regular or irregular. So it is regular shape by d squared over 4 times L. This is for the regular core plug. So now for the porosity measurement, you can say actually in a core plug or any rock that you have, you will find pores actually inside. So you can see this hole, this tiny hole. So the white one here is the grains that you have in the rock or the core plug, and the black one here is the pores available for the water, for the oil, for the gas to be inside this core plug. And actually, this is the void space. Once you clean this core plug, if the core plug contain water or contain oil, if you clean it, it will be a void space with just the gas filling this space. And actually, if the grains is very big, like this large one, this is large grains, you can see there is actually porosity inside these grains. So there is big porosity here, and this is a small pores here, micro pores. Again, this is a photo of so this is the grains, and the black one here is the pore. This is the pore. Actually, this is the reverse. So the black one here is the uh, pores, and the void is the grain. So they reversed it to see how it is connected. And I come back to this photo again. Okay. So you have the rock. So the rock actually is like the pore is like a room. So if you imagine that you are standing in a room with the walls, with the door, And so it is actually the bore is like a room, and the walls of the room is like the grains that you have in this core block or this rock. So if you are like, if you imagine yourself like a drop of oil, so the drop of oil will be in the middle of the room, in the middle of the pore space, and you have like a wall or grains around you. So how you are going to come out of this room? You have to get a door. So to come out, for a drop of oil to come out of the pore, there should be a door to come out of from. So this door is the throat. Okay. So to come out, you can it should be at least two doors. Okay. One door to enter and the other door to come to get out of. Okay. So for an oil drop to come out of a pore, there should be at least two doors. One for in and one for out. So the pores that we have in a core, it could be connected. Okay. So the connected pore can have water in, can have oil in, and so on. And it could be unconnected pores, separated island of pores around this core plug. So actually, this is not measurable for us using helium porosity, using normal um, uh, helium porosity, and it is called effective porosity. Let's talk um, experimental wise or scientific wise definitions. So all the pores that you have in a core plug, it could be connected or unconnected or unconnected or isolated. If this pore is connected, it is called effective porosity. Effective porosity. This means that once the oil or the water or the gas come in, it can come out. But if it is isolated, this means that what is in will be remaining in as long as the core is not touched. So this is isolated pores. This is actually connected pores. This is isolated, isolated, isolated. So can I measure this amount of this isolated? Actually, yes, I have to crush this pore. So now it is destructive test. So now I destruct this core plug is no longer will be in use, and I can no longer use this core again because it will not be the same shape that I have. So the porosity actually is the volume of pore or the pore volume divided by the bulk volume. So the bulk volume that I measure for this core is actually this one. So the bulk volume is the pi d squared over 4 times L. So this is the volume of the core plug. This is the bulk volume. What is the pore? If I measure the porosity, I can know the volume of pores that I have. Okay? Or the reverse. If I have the pore volume divided by the bulk volume, I can know the porosity. And actually, it is dimensionless because volume over volume. How I measure porosity? Actually, I can measure the porosity using helium porosity device. All what you have in this helium porosity device, there is different version. You should have like a cup here, like a cup like this one, the metal cup that you will place your core plug. It can be regular shape or irregular shape. So the porosity can be measured for regular shape and irregular shape. So once you place, you have actually to measure the bulk volume of your sample first, and then you have to place it in the cup. Then you have to close it to seal it. Okay, so you have to with this handle. This is a hydraulic uh, machine or something. So it will close this cup like here. So what you have here is you are going to close this cup. But this cup it is connected externally with a stainless steel tube to a helium reservoir, and there is a valve to close and in to the in and out. So it is connected here, and there is a valve here. It is connected, and there is a valve. It's in the diagram here, it is connected and there is a valve. And it is connected, this valve actually connected to a helium reservoir. So this helium reservoir is allowed to expand to this cylinder that is containing our core plug. Using Boyle's law, which we have V1 equal P2 V2. I'm not going to discuss how we like calculated the Halley porosity uh, equation, but in general, this is a principle. P1 V1, so you have P1 V1 in this container. After you have helium expanding, you have V2 V2 using both volume of the containers, okay, and the pressure. So the porosity, now you have the pore volume, the pore volume divided by the bulk volume, and you can calculate the flow. Okay, so some devices just to give you a reading for the pressure, a reading for pressure out of pressure in, you know, the volume V1 and V2, and then you can calculate the pressure, you can calculate the volume and calculate the pore volume, and then do the porosity. Some devices just automatically will display the porosity. Okay? So according how advanced your device would be. But it's helium porosity is very simple experiment, just straightforward, no complications in this experiment. And actually, we do most of the time we do helium porosity because actually helium is very tiny, so it's a tiny molecule that actually it can diffuse and go occupy the tiny pores that you have in your core plug. So this is why we will choose helium because actually it's a very small size molecule that can diffuse to a very, very tiny pores available in your core plug. The second measure experiment that you have is the water oil saturation. Is again, it's very important to know the saturation, the amount of oil, the amount of water that you have is very important. Uh, because actually this will judge what is actually the reserve of oil that you have, what is the reserve of gas, what is the reserve of oil. So the saturation is the volume of fluid that is occupying here, as you can see here. So this is the white one here is the water, and the small one, I'm sorry, the blue one is the water, and the white one is the oil. So we need to know what is the amount of oil available, what is the amount of water that you have. So the initial saturation is the volume of fluid divided by the pore volume. It's the same for the oil, volume of oil divided by pore volume. So how we are going to calculate the pore volume using helium porosity. We already calculate the pore volume. What is the volume of oil? This is what we are going to do now. What is the volume of water? What is the volume of gas? So the volume of oil is the saturation of oil, not the saturation of water. The saturation of gas should actually be 1 because all of them is fraction. It ranges from 0, each one of them will range from 0 to 1. The device that we are using for oil for fluid saturation is then start distillation. The first thing is it is non-destructive, so you can still use the core plugs that you have. We have to use it's better to use regular shape one. Still, we can use irregular shape, but it's better to use regular shape one. Core plug. You will place this core plug. You have the weight of this core plug, and it will be W1, and then you will place this core plug inside this dense dark apparatus. You will have a solvent here, so the solvent will evaporate and it will heat up the oil, the water that is available, and go to the top, and then it will condense. Go to the top here, and it will condense here. So you have the toluene, and then you have the water because water it does not dissolve in toluene, and it will separate. So the water here, so we can know the volume of water that you have, the volume of formation water that you get divided by the pore volume. Now you can know the water saturation. So Or what happens is the toluene is heated. As the toluene go on the top, it will dissolve the oil, heat up the water. All of them will be evaporated to the top and then condensed here, and we group this, collect the toluene and the water in this graduated cylinder, so we can know the amount, the volume of water. Okay, but we know the volume of water. What about the oil? Now we can get, because it is non-destructive test, we can just get this core and clean it. Clean it using Soxlet. So again, so the methanol in this methanol and toluene mixture, we add the core plug here in the Soxlet. As we heat this toluene and methanol, it will evaporate to the top and then condense it drop by drop, clean the core from any oil, any water available, and go to the reservoir back again. So once we finish, like it is it's like a different runs. Once we finish, once we cleaned our core, we get it and we put it in a vacuum oven. So the vacuum oven here, because we want to make sure that the core is clean, there is no water in this core, there is no residue of solvent. We have to heat this core and place it using an oven. But we are using vacuum because we want to heat it at lower temperature. Like if you imagine that you have a water will evaporate at 100 degrees Celsius at normal atmospheric pressure. But actually, if you lower the pressure, the water will evaporate at temperature lower than 100 degrees. So now you clean the core and then leave it uh, to um, to cool down, and then you have to wait it. So this is W2. Using the equation W1 minus W2 minus the weight of the formation water. Now you can know the weight of oil. If you know the density of oil, we already discussed how we measure the density. You can know the volume of oil. You can calculate the saturation of oil, volume of oil divided by the pore volume. For the gas saturation, 1, because we said that saturation of water plus saturation of oil plus saturation of gas all together equal 1. So saturation of gas equal 1 minus saturation of oil plus saturation of water. Now we are going to go through the liquid and gas variability. Actually, it's very, very important test. And it's a slightly complicated. So now it's going to a complicated, slightly complicated, not very complicated, but slightly complicated test compared to porosity measurements, saturation measurement, because now we are going to deal with Hassler core holder. Again, we have to, because we are using Hassler core holder, we have to get a regular shape core plug. We have two types of permeability. The absolute permeability, actually, when just like one liquid is inside, just or not necessarily liquid, it can be gas, one fluid is inside. Oil, just brine, just nitrogen or air inside this core block or the rock. The other type is the effective permeability. It's we have one phase, or we'll study how one phase is flowing with the presence of two or more fluids. In this case, this is effective permeability. We are going to talk about absolute permeability. Effective permeability is actually more complicated. So absolute permeability is slightly complicated. Effective permeability is more complicated, and of course, relative permeability is the most complicated one. So for permeability is measured using Darcy law, which we have the flow rate, the permeability area, pressure in minus pressure out, viscosity, and length. So the viscosity, we already to calculate the permeability, you cannot do so without knowing the viscosity of the fluid that you have. Okay, or the fluid that can be gas or liquid, but we are going now to talking about gas. Sorry, liquid. Okay, so to study the steady state, so it is steady state because there is other type of permeability called unsteady state. The simplest one is a steady state liquid which means absolute, just liquid, absolute permeability measurement. We are going to use Darcy's law. But how we are going to do this in the lab? We are going to use a core holder. So this is the core holder to hold the core plug, that the regular shape core plug in place. This will make sure that the flow is directional flow, okay, not a radical flow. Sure. Oh, okay, it's not. I will go through the core plug later. Yeah, it's not available here. So it is. We have the core plug here, and then this is a pump because we have pressure. We have uh, a pressure regulator to read the pressure. Here another pressure regulator. This is a confining pressure, and this is accumulator. This is the pump that we have. This is the back pressure valve that we have, and this is another pump, and this is the core holder that we have. Again, this is a shape that we a constant flow injection pump. This is a type of pump that we can use. This is the shape of the core holder. This is shape of another shape of a pump. Okay. This is a pressure reader or regulator, digital pressure, back pressure regulator. So for the core plug, why we are using core plug? Because actually we are going to place core inside. We are going to place a core sample inside here. So irregular shape. And then this is the inlet. We have the flow just entering inside the core in this direction. And from the surrounded, the core sample is surrounded by a Vulcan sleeve, okay, to prevent any bypass of the fluid to be to be radical flow. No, we just have to get the flow in this direct way, okay? I mean, entering from the left to the right or from the right to the left, whatever. So this is why it has to be we are applying the pressure. So there is a fluid here, water, applied to this bottle sleeve, applied to this core to prevent any flow going to an in a radical way, just direction flow. Okay, and the plug here that we have entering the pool, it is distributed. So there is many ports we can inject the fluid through, and it is distributed, so it is going through all the phase of the core sample. So the first step here is to load the core plug, and then we apply confining pressure to prevent any radical flow, and then we apply vacuum to clean the core from any air because we don't want to have interference, especially if you have a liquid. The other step here is to inject the gas that you have, and the last one that you apply according to the factory change the back pressure, so you will get different pressure delta B, different delta B. You will have the flow rate, the pump injected at a zero point, for example, 0.5 milliliter per minute, you 0.4 milliliter per minute. So you change the flow rate of the liquid that you are injecting. Now you can calculate and draw, yeah, because you did different tests at a different flow rate. So you have the flow rate that you have divided by the area constant, the flow rate we are changing, and then delta P is it changing according to the change in the flow rate. The length is constant. You'll draw Q over A on the y-axis. On the x-axis you have delta B over L. So you will have a straight line. The slope of this straight line is Q over U is viscosity. K is actually the permeability, the liquid permeability, the absolute liquid permeability that you have. So this is an example of what we can measure here. So you have a core plug of the density 5 centimeter and the length of 10 centimeter. You have the viscosity, so 1.6 centibars. After running, you have measurement different flow rate, changes the flow rate according to the change in the flow rate. You have B1, a different inlet pressure, and the outlet pressure is is zero actually. It's atmospheric. So using this experiment, using this equation, we can draw, and actually you can calculate what is the, on the y-axis you have Q over E. So you calculate using the data. You will calculate the A, then divide Q over A. You have a different data. You have straight line. You can measure the slope of this straight line and get the liquid oil permeability. In this case, it's oil permeability. The steady state gas permeability is um, more simple than using liquid, because actually you can just use a gas cylinder. But what we have is to reconstruct the Darcy law to accommodate for the expansion of the gas, because actually the liquid, the pressure decrease, the liquid will not expand as what happened to the gas. So at high pressure the gas will occupy certain volume, but as you go to the end of the core, or to the exit of the core, the pressure will decrease and the volume of the gas will expand. To accommodate for this expansion, we apply Boyle's law, and we get the gas permeability equal to times the flow rate times the pressure inlet times the viscosity of the gas times the length divided by the area of the core plug, times Py square, P inlet square minus P exit square. To do this experiment, we have to have a gas cylinder, flow meter, a pressure transducer or holder, and back pressure regulator. We have to measure the pressure in and the pressure out. So we either you have to get delta B pressure regulator, or a pressure regulator here and another pressure regulator here. So this is the gas cylinder, this is the flow meter, this is the back pressure. We already saw the core holder. So the first you have to load the core holder, pressurize your core, and then you have to inject the nitrogen, adjust the flow meter to different flow rates, and then measure the delta B and substitute in this equation. Okay, but can we use this gas permeability to know the liquid permeability? Because actually you want to know the oil permeability, the water permeability. The gas permeability is not the one that you want to calculate. You don't want to know. So the first is yes, actually the answer is yes. We can, using Klinkenberg effect, they find that as you increase the pressure increase, actually the permeability actually will reach, as you have different gases, as you increase the pressure, your permeability will decrease until you reach a certain value at zero pressure. Okay, or infinity pressure. So actually this is because the gas leverage effect. Normally, when you are having liquid flowing in a tube, the liquid near the tube will have zero velocity. But in the case of gas, the liquid near the tube wall actually is not doesn't have a zero velocity. It has a velocity. It has a reading for a velocity, which is called the gas slippage effect or phenomena. So we find that as you increase the pressure, you can overcome this phenomenon. So they say that the gas permeability, there is a relation between the liquid permeability and gas permeability. The liquid permeability equal gas permeability minus the slope divided by mean pressure. And the mean pressure actually, I showed the mean pressure. This one minus this one divided by this one, divided by 2. So, so the slope, if you measure, if you draw the gas permeability that you have here, and on the y-axis and on the x-axis, you draw 1 over v mean pressure, then you will have the slope. So this slope divided by the liquid permeability, you will get, I'm sorry. So if you have the slope here, and then divided this slope by the mean pressure, you can, and you already have the gas permeability, you can calculate the liquid permeability. And this is what we want. The last experiment that we are going to talk about is the contact angle and the interfacial tension. So the wettability is very important actually because it will show you which phase will which liquid will be in contact with the rock that you have. So if the rock is water wet, what is going to happen is the water will be the favored phase to be in contact with the sand or the sand grain that you have. So it will actually, if you place a drop of water over a sand that is water wet, the water will spread, and we will have a contact angle between the surface of the sand and the oil or the air that we have through the water, measured through the water here, less than 90 degrees. So this means that it is water wet. So what actually, if we have an oil wet and we place a drop of water on it, we will have a contact angle. It will be like a ball, and the contact angle will be higher than 90 degrees. Okay. And actually, the favored phase to be in contact with the sand will be the oil, and the oil will occupy the larger pool. Okay, the water will occupy the larger pool, but the oil will occupy the smaller pool. The intermediate wet, which means that it is neither water wet, neither oil wet. It is like intermediate wet, something between 90 degrees, and it's around 90 degrees Celsius, 90 degrees, and not Celsius, 90 degrees. This means that it is neutral or intermediate wet. There is other types called the mixed wet, which means uh, mixed wet that some part, like if you look here, this is clay, this is a clay, and this is silica. So, and this is drop of water. So you have found that the drop of water is actually spreading over the silica. So if we measure the contact angle between the silica and the oil here, you will find it to be water wet. But on the clay here, the water is like a ball. So it is oil wet. So the same sand, the same core block, it can be some part will be water wet, some part will be oil wet. So in this case, it's called mixed wet. So this is the oil media, this is water, and this is quartz grain, this is clay, and this is water. We can do this experiment using high pressure apparatus, or you can you do this experiment on atmospheric. Um, uh, for the contact angle, we use test called Cecil drop test. Static contact angle, we just place a drop of oil, um, or in this case, a drop of water and this is air, and this is the surface. So we find that there is a contact angle. We can measure the contact angle. This is a drop of oil. We have a drop of water, whatever the drop that we are using, and it doesn't make any difference. So according to the test, according to the surface that you are using, according to the fluid that you want, it doesn't differ. It's just a drop of water over surface of called scissor drop, and then you measure the contact angle and this drop of this drop has to be over a size from 3 microliter to 10 microliter. Normally, I do 5 microliter as a constant size for the oil drop or for the water drop. Reverse sessile drop, if you are doing a water oil test, what is going to happen? If you place a drop of, if you have a oil water media and you are placing a drop of oil, because the density of oil is lighter than the density of water, the oil will float to the top. So you will not be able to have, if this media is water, you will not be able to have oil sitting horizontally like this on the bottom of the container that you have. No, it will float to the top. So what we are doing, we are using a hooked needle to place an oil drop, and we are it's called a reverse sessile drop or reverse sessile drop. So the solid now will be on the top of the container, and this is a hooked needle. We place an oil, and this is the water. We can measure the contact angle. That's fine. It's the same way. For the interfacial tension, we use bend and drop test. So the bend and drop test is placing the drops that you have according if you are placing it on in air, it's called surface tension. If you are placing it in another liquid, so oil in water, it's called interfacial tension. So a water drop, an oil drop, surrounded by air, surrounded by CO2, surrounded by nitrogen. In this case, it's surface tension, and it's called the bend and drop. And you can calculate the surface tension for this drop. For the interfacial tension, what we have here, it is an oil, okay, in water, and this is why it is the oil is like a ball here, because it is due to the buoyant force. The oil want to float to the top, so it is like it's not a eye shape or a water drop shape like this one. So in the north, we are doing this using a hooked needle to get the eye shape one, the shape of not the shape of the ball. This case is this is a incorrect test. It should be hooked needle with the oil getting a shape like an eye or water drop like this one, but I reversed it. So in this case, we are using reverse bend and drop, this one, like this one. This is the hooked needle, and in this case, this is the oil surrounded by water. So it is getting the shape, or it's called tear shape or water shape or whatever shape. So this is the shape that we want. So this is a reverse bend and drop when we are building oil and water. And this is the high pressure we can do in this case. This is the clear glass. You can see what is happening inside, and this is the camera that is monitoring what is happening. And you can do surface tension, interfacial tension, contact angle measurement. Just you are placing using bombs, and you are placing the liquid that you want, the oil that you want, and the rock sample that you want inside this container, and you are increasing the pressure and doing your measurement. And I'm not finished. Uh, thank you.
Dr. Rehab, you have two questions in Q&A section.
Okay, yes. So the first question, uh, is there any other type of fluid properties that needed in different types of experiment? Yes, there's been many fluid properties that is required. It's not I'm not displaying like exclusive test. No, it's this is a sample of the test that you can do for fluid properties. There is other tests, but it is ranging in the importance. Okay, so you have to define which one you want according to the important. Is it important for your measurement, for your calculation? So you can choose. Can we have the slides? I think it's fine. Yeah. Maybe I don't know the policy that you have here, but we can discuss this with Dr. Ahmed. Uh,
Dr. Rehab, actually, I have one question.
yes.
For determining oil saturation, we have to use chocolate extractor in a mixture of solvents. So, how long time it takes this experiment, and how many rounds?
Okay, so it is,
Yes.
I don't calculate it for the toxalate experiment. I don't calculate it with how many rounds because you don't know the rounds. You are not just near the, you are not closely monitoring it. No, just leaving it for, yeah, roughly 8 hours. Okay, so you make sure that you adjust the toxalate heating mantle to the proper temperature to evaporate the solvent, and you like sitting next to it until you make sure that it's evaporating and condensing and everything is working. Once you are confident that everything is working, you will leave it for 8 hours.
Okay, thank you so much.
You're welcome.
Actually, you have another question in Q&A section.
Okay. If the pressure differential does not stabilize after two bore volumes and continue to increase as the fluid injection proceeds, should the injection continue or should the flow rate be changed? Can less than one bore volume be used to determine the pressure differential? Okay, usually we do three bore volumes, five. So I don't measure the permeability until I um, flow three bore volumes at least. Then you have to make sure that everything is stable, that all the pores are filled with the fluid that you are injecting. And usually it's not a very stable. You are not getting a very stable reading, but you are getting a small fluctuation. So a small fluctuation is accepted. And if it is, if you are talking about gas permeability, I'm not sure which permeability you are talking about, but a small fluctuation is accepted, and you can do if you have the flow rate that you are doing your permeability on is not very stable, it's not getting you a stable result. You can change it. It's fine, but don't increase the flow rate to a very high to get a very high pressure, okay, because actually you can break your full plug. You have to make sure that the flow rate that you are using is not getting you a very high pressure difference, because what I monitor is the difference. You don't have to get like higher than 200 psi difference or 300 psi for the maximum, okay? Because you are going to have your core plug broken. Okay, so this is my answer. Can less than one pore volume be used? No, it's better to have at least three pore volume, and this is what was used in the literature. So for myself, I do five pore volume at least, but from the literature, they say that at three pore volume it is getting stabilized.
Thank you, Dr. Rehab, for this session. It's so instructive, and I hope we can meet next session, inshallah.
Inshallah. For the next session, we are going to talk about the crude oil, the distillation. It's like the refinery and the petrochemical and uh, gas engineering. Okay, thank you so much.